Welcome to Lecture 8. In this lecture, we'll talk about inner product and related ideas. Now, the inner product, there are various kinds of inner products, or various ways of defining inner products, and that is discussed in your book. But the one that we're interested in is the one that's most usually used, and that's the dot product. And the way that the dot product of two vectors is defined is the following. Let's suppose that the vector v is equal to v1, v2, vn, and the vector w is equal to w1, w2, wn. In other words, the components of v are v1, v2, vn, and the components of w are w1, w2, wn. Both of these vectors are assumed to be in Rn or Cn. They're in, and so if we want the dot product of those, it is denoted like this. We'll say dot product of v and w is denoted as v dot w, and I'm going to put bars over these, which is frequently done for vector quantities. And the way that the dot product is defined is equal to v1 times w1 plus v2 times w2 plus plus vn wn. So you can see from this definition that it would not make sense to take the dot product of two vectors that have different dimensions. In other words, it would not make, for instance, sense to take the dot product of a vector from R2 with a vector from R3, because one would have two components and the other one would have three components, and therefore you couldn't form all the necessary products here that you need in computing the dot product. So this is how we define the dot product of two vectors. Now, there are some interesting related ideas here. Let's define the Euclidean norm of a vector v. The Euclidean norm of v is denoted frequently like this, with v with two bars on either side of it, and it is equal to the square root of v dotted with itself. And so this would be the square root of v1 squared plus v2 squared plus plus vn squared. So for example, if v were the vector in R3 given by 1, 2, 3, then the Euclidean norm of v is equal to the square root of 1 squared plus 2 squared plus 3 squared, which is the square root of 1 squared is 1 and 2 squared is 4, so that's 5 and 9, and we'd have the square root of 14. So that's how you calculate the Euclidean norm of a vector. And another interesting idea that's related to the dot product is the following. It turns out that when we calculate v dot w, if v and w are two vectors, then v dot w is equal to the norm of v times the norm of w times the cosine of the angle between v and w when you put the two vectors v and w tail to tail. So the idea here is that maybe one of these vectors is v and the other one is w, and we line up the vectors tail to tail. You can see that their tails are touching right here, and if we orient the vectors in that way and we define the angle theta between them like this, then the relationship between v and w and the norm of v and the norm of w and that angle theta is given by this equation right here. And of course, obviously, we could solve for theta in the following way. We just divide each side of this equation by the norm of v times the norm of w, and then take the inverse cosine of each side, and we get this formula. So this formula allows you to calculate the angle between two vectors. And one more related idea here is that this gives us a way of finding out if two vectors are perpendicular to each other. The way this goes is the following. Suppose that v and w are two vectors such that the norm of v is not equal to 0 and the norm of w is not equal to 0. Okay, and if we're in a real vector space, then this simply means any vector that is a non-zero vector. Now, in a complex vector space, you can have vectors that have a norm equal to 0, even though they're not the zero vector. So that makes things a little, you have to give a little more thought to those situations. But in a real vector space, like, for instance, let's say in Rn, the only way that the norm of a vector can be 0 is if it's the zero vector itself. So, to complete this thought, then, we say, suppose that v and w are two vectors such that the norm of v is not equal to 0 and the norm of w is not equal to 0. Then, if v dot w equals 0, we can conclude that v and w are perpendicular. I.e., theta equals 90 degrees. And you can see that because if v dot w is equal to 0, that would mean the left-hand side of this equation here is 0, which means then that the right-hand side must be 0. But if the right-hand side is 0 and neither one of these norms is equal to 0, then that must indicate the cosine of theta is 0, which means that theta is equal to 90 degrees. So, so you can see here from just what we've said so far that the dot product is a very useful tool to know about. It can tell you, it can help you to decide the length of the norm of a vector, and it can also help you to find the angle between two vectors, and in particular, it can help you to determine if two vectors are perpendicular to each other. Another word for perpendicular is orthogonal. So this is a very useful tool to know about. And now let's look at a couple of problems from the book. Let's look, for instance, at problem 15 excuse me, we'll say 7.9.18. And they want us to find the Euclidean norm of the following vectors. So I'll write this: find the Euclidean norm of V if, and the vector that they give us for V in this problem is -4, -8, -1, and then T. Now remember that T means transpose, so that means that that V is given by that, -4. Oh, and I've actually copied down, this should be +8 here. So -4, 8, -1. And it's very easy to calculate the norm of V. It's simply the square root of V dotted with itself. And so that's the square root of -4 squared plus 8 squared plus -1 squared. And so that's the square root of -4 squared is 16, and 8 squared is 64. 16 and 64 is 80, and then -1 squared is 1, so we have 81, square root of 81, and that is equal to 9. So the length of this vector, or the Euclidean norm of this vector, is simply 9. And that's, I think you agree, very simple. And now let's look at a more challenging problem. It says problem 7.9.22. And we're asked to find all vectors in R3 orthogonal to 2, 0, 1. And furthermore, we're also asked, do these vectors form a vector space? So this is really an excellent problem to review the idea of orthogonality, which we've just seen above, and also to review the concept of vector space. So I very strongly urge you to turn off the video and try to do this problem on your own first, and then once you think you have it, come back and we can work on it together. Okay, so I hope that you had some luck working on that problem, and let's now see how it would go. So we want to consider all vectors in R3 that are orthogonal to 2, 0, 1. So let's just say let V equal x, y, z be a vector in R3 that is orthogonal to 2, 0, 1. By the way, this example I think is very important. I would not be surprised at all if you see it again in the future. So do pay careful attention. Okay, so if this vector x, y, z, this is a general vector in R3, is orthogonal to 2, 0, 1, well, what does that mean? Well, that means that x, y, z dotted with 2, 0, 1 is equal to 0, as we've said above. If the two vectors are orthogonal, means that their dot product is equal to 0. Okay, and now if we go ahead and compute the dot product of these two vectors, we get 2x plus 0y plus z is equal to 0, and of course the 0y can drop out, and we just have 2x plus z is equal to 0. So now we're in a situation that's really quite similar to something that we've already looked at in a previous section. And let's go ahead and point that out. So we are interested in all vectors x, y, z in R3 such that 2x plus z is equal to 0. Now I'll ask, is this a vector space? And I hope that when you worked on this problem on your own, you remembered that to check to see if something like this is a vector space, what we want to do is check for closure under scalar multiplication and closure under vector addition. So let's check that. Let's say closure under scalar multiplication. Okay. And remember, to do this, we assume, now let's go ahead and call this set, because we need to give this set a name. So I'll say, let's call this set of vectors capital V. That's a notation we used earlier, so I'll just use the same notation. So we're going to call the set of all vectors in R3 that satisfy the equation 2x plus z equals 0. We'll call that V. And we want to know now, is this a vector space? And so we check for closure under scalar multiplication in the following way. We will assume that little v is any vector in that set capital V. Okay? And so now we ask, is, well, we are also going to assume and that lambda is any scalar. And now, remember, if v is any vector in V and lambda is any scalar, then closure under multiplication means that for any such vector and any such lambda, V is closed under a scalar multiplication only if lambda V is also in the set. So we ask, is lambda V in V? Okay? Well, let's see. If V is equal to the vector with components x, y, z, then lambda V is the vector with components lambda x, lambda y, lambda z. And now we want to ask, is lambda V in the set V? Well, remember, the constraint that vectors in V must satisfy is that 2 times their first component plus their last component is 0. So asking if lambda V is in V is equivalent to saying, is 2 times lambda x, that's 2 times the first component, plus the last component, is that equal to 0? And as usual, as we did before, I'll put a question mark over the equal sign because we don't know if this is equal or not. Well, now if you multiply out the left-hand side of the equation, you get 2 lambda x plus lambda z equals question mark 0. And so this becomes lambda times 2x plus z equals question mark 0. And now we see that, now remember, this is supposed to be, we're checking to see if this is going to be true for any lambda. And so for this to be true for any lambda, it must be the case that 2x plus z is equal to 0. But that is exactly what we already know, because if this vector little v is in the set capital V, then that means it satisfies the criterion 2x plus z equals 0. So since we know that 2x plus z is equal to 0, then we can write lambda times 0 equals question mark 0. And of course, that will be true for any lambda. So this set, capital V, is indeed closed under scalar multiplication. Now let's check for closure under vector addition. We need to check for both in order to make sure that it is a vector space. Okay, now to check for closure under vector addition, remember what we do is we pick any two vectors in the set. So we'll let assume we'll call them V, and this time I'll assume that the components of V are V1, V2, and V3, and W, and I'll make the components W1, W2, and W3. We assume that those are two vectors in V. And now, in order to check for vector addition, closure under vector addition, we have to ask, is V plus W in V? That's the question. Well, V plus W is equal to V1, V2, V3 plus W1, W2, W3, and that's equal to the vector whose first component is V1 plus W1, whose second component is V2 plus W2, and whose third component is V3 plus W3. And now we ask, is this in V? And remember, the way you determine whether or not something is in V is to check to see if twice its first component plus its third component is 0. So we say, is 2 times V1 plus W1 plus the third component, which is V3 plus W3, is that equal to 0? And now let's multiply out on the left-hand side. We have 2V1 plus 2W1 plus V3 plus W3 equals question mark 0. And now rearrange and make this 2V1 plus V3 plus 2W1 plus W3 equals question mark 0. And since the vector little v is in capital V, it must be the case that 2v1 plus v3 is 0. And since the vector w is also in V, it must be the case that 2w1 plus w3 is equal to 0. And so this becomes, the question is 0 plus 0 definitely equal to 0? And of course the answer is yes. So we have closure under scalar multiplication right here, and closure under vector addition, and so V is indeed a vector space. And since V is a vector space, it makes sense now to talk about the dimension of V. Now the underlying space, all these vectors are in R3, so the dimension of V is 3 minus the number of constraints. And the number of constraints, remember, V is all vectors in R3 with just this one that satisfied this one constraint. 2x plus z is equal to 0. So the dimension of V is 3 minus 1 or 2. The dimension of V equals 2, and therefore any basis for V will have two linearly independent vectors in it. So basis for V. All we have to do here is to find two linearly independent vectors that satisfy the equation 2x, I'll remind you here, 2x plus z is equal to 0. And a very easy way to get this is to say 0, 1, 0. That is definitely one vector that satisfies this equation. And then 1, 0, negative 2 is another vector that satisfies the equation. And definitely these two vectors are linearly independent, and therefore this is a basis for V. And now we can finally answer the equation, the question in this problem. So the set of all vectors in R3 that are orthogonal to the vector two, 0, 1 is the vector space V, which has the basis zero, 1, 0, 1, 0, negative 2. And then I'll put in just one more note. Note that V is the set of all linear combinations of the two vectors 0, 1, 0 and 1, 0, negative 2. And I'd like to elaborate that on for just a moment before we end. Obviously, those two vectors are orthogonal to 2, 0, 1, because if you take the dot product of 2, 0, 1 with 0, 1, 0, you definitely get 0. And if you take the dot product of 2, 0, 1 with 1, 0, negative 2, you also get 0. So these two vectors are both orthogonal to 2, 0, 1. And the set of all linear combinations of those two vectors means any vector that can be written as alpha times the first one plus beta times the second one. So this set, the set of all vectors, all linear combinations of these two vectors, that is the set V here, and that is the complete set of all vectors in R3 that are orthogonal to the vector 2, 0, 1. And the final thing I'd like to say is that this set V is actually a plane. Here's a vector, and V is the plane that is perpendicular to this vector. So for instance, in a rough sort of way, we have some plane in R3. Now, of course, this is not a real accurate depiction of a plane because a plane is infinite. It doesn't have boundaries. But I hope that at least this suggests the idea. So there's the plane, and here is the vector 2, 0, 1. So that vector is perpendicular to the plane. And that's the idea. The plane is V, and 2, 0, 1 is perpendicular to the plane. So that's the idea of this problem. So that concludes our discussion for Lecture 8. And now let's find some problems for you. Okay, so the problems for Lecture 8 will be as follows. Problem 8.1 is simply problem 7.9.15 from your text. And that's a very straightforward problem. It just involves calculating the Euclidean norm of a vector. So very straightforward. Problem 8.2 says the set of all vectors in R3 that are orthogonal to both 1, -1, 1 and 2, 0, -1 is a vector space. What is the dimension of this vector space? Choice A is 0, choice B is 1, choice C is 2, and choice D is 3. And then finally in problem 8.3, you're dealing with the same set of vectors. So again, it says the set of all vectors in R3 that are orthogonal to both 1, -1, 1 and 2, 0, -1 is a vector space. Circle each that is a basis for this vector space. So there may be more than one answer to circle here. There may be no answers to circle. You'll need to decide, but the choices are A. In A, we have two vectors, 0, 0, 0, and 1, 3, 2. In B, we have a set consisting of just the one vector, 1, 3, 2. In C, we have a set consisting of two vectors, 1, 3, 2, and 2, 6, 4. And in D, we have a set consisting of just one vector, 2, 6, 4. So those are the problems for Lecture 8, and that concludes Lecture 8. So good luck.